Hello and welcome to this calculus video. Today we will be talking about antiderivatives.
Math 112.
We have spent considerable effort to develop techniques to compute the derivative of a function and to use the derivative to answer a variety of questions about the function being differentiated. We also know that in practical scenarios, the derivative has a practical meaning. For instance, if a function tracks the displacement of an object moving along a straight line, then the derivative of that function with respect to time measures the object's velocity. What if, instead of giving you a function and asking for its derivative, I gave you the derivative and asked you to recover the original function? In our scenario above, we could imagine watching the speedometer of a car, which measures its velocity. How could you recover the displacement of the car from knowing its velocity? What we want is a function whose derivative is the velocity. We want to reverse the process of differentiation. A function big F whose derivative little f is known is called an antiderivative for little f. Saying that the derivative of big F is little f is equivalent to saying that the antiderivative of little f is big F. Let's look at an example. Suppose our function is little f of x equals x squared. If you keep the power rule for derivatives in mind, it isn't hard to discover that big F of x equals a third x cubed is an antiderivative for little f, because if we differentiate big F, then we get little f. However, a little more thought tells you that g of x equals a third x cubed plus 10 is also an antiderivative, because when you differentiate, the plus 10 becomes a 0. More generally, any function in the form a third x cubed plus c for constant c will be an antiderivative. So if we find an antiderivative, we can add an arbitrary constant to it to get another antiderivative. This leads us to a natural question of are there more antiderivatives that aren't in this form? The mean value theorem tells us that any two antiderivatives of a function differ by a constant, so we actually have an exhaustive list. If little f is a function defined on an interval I, and big F is an antiderivative of little f, then the most general antiderivative of little f on I is big F of x plus c, where c is an arbitrary constant. Here are some specific examples. The most general antiderivative of cosine of x is sine of x plus c. The most general antiderivative x to the n, for n not equal to minus 1, is x to the n plus 1 divided by n plus 1. Sometimes, instead of finding the most general antiderivative, we want a particular antiderivative that has some property. Usually, we want an antiderivative that has a particular y value at some specified x value. This extra property is called an initial condition. The problem of finding a particular antiderivative passing through a particular point is called an initial value problem. These are examples of problems called differential equations, which we will see more of later. To solve an initial value problem, we find the most general antiderivative, and then use the initial condition to find the value of c that works. For instance, suppose we want to find the function f of x which satisfies that f prime of x equals e to the x plus 2x, and that f of 0 is 2. Firstly, we find the most general antiderivative of f prime of x, which in this case is e to the x plus x squared plus c. You can check this by differentiating. Now we need to find the value of c. We plug in x equals 0 and set this equal to 2, and find that e to the 0 plus 0 squared plus c is 2, and so c equals 1. Therefore, our function is f of x equals e to the x plus x squared plus 1. That's all for now, folks. Today we introduced the notion of an antiderivative of a function. We found the most general antiderivative of a function and solved initial value problems where we want a particular antiderivative.
Math 112.